This video goes through the process for finding an approximate solution for the relativistic orbital shape equation by making use of perturbation theory. It then uses the result to derive an expression for calculating the angular precession for a body or particle with mass in orbit around another. This video also demonstrates graphically how orbits in general relativity do not close. So here we go. In a previous video titled Schwarzschild Geodesics 7, we saw that orbits for particles with mass do not close, but instead they precess. And so we see these ellipses here rotating round and so on as we go around. Now the semi-major axis rotates about the focal point where the central mass is located, and you can imagine here the semi-axis along this one here, and then you can see the next iteration, the next orbit, it's over here. And what we're interested in is we want to determine the amount of precession, delta phi, per orbit. So here we go, semi-major axis here on the first orbit, then on the second orbit it's over here. What is this angle of precession? Can we calculate it? And that's what we're aiming at. So first we'll solve the relativistic orbital shape equation, come up with an approximate solution, and then from that derive an expression for this delta phi, this angle of precession. Alright, so coming back to an ellipse, what are the basic properties of an ellipse? So here we have our mass, here's our smaller mass here, or some other mass, m0. It's orbiting this bigger mass m at the foci here. Here's the radius, the separation here, the distance here, the separation here is the angle. R is a function of phi as the object follows an ellipse. Now in Newtonian mechanics, this is R as a function of phi. The orbits close and it stays and it follows the same ellipse repeatedly for as long as it's in orbit. That could be any number of iterations. So I'll just cycle through and just stay in this ellipse. Perihelion over here at this point here, and aphelion over here. The distance r min of perihelion is the semi-major axis A here times 1 minus the eccentricity E. Over here, this distance from here, from the mass to the other to aphelion, is r max, and that is the semi-major axis times in brackets 1 plus the eccentricity. So in Newtonian mechanics, the shape equation is this second derivative of u, and plus u is equal to this constant over here, where u of phi is 1 over r of phi. U is 1 over r, as we've seen in previous videos. Alright, now in the previous video we found the relativistic orbital shape equation to be this object here. The Newtonian case is here, plus this n correction term here, this relativistic correction term over here. And we will attempt to solve this and come up with an approximate solution for this. Now this is different to the Newtonian form, which has as its solution this object here, that, E the eccentricity, the angle phi, angular momentum here squared, the mass of the object in orbit, and the central mass around which it's orbiting here, and Newton's constant g. Now for the relativistic case, we seek a solution using perturbation theory, which in general has the form u is u0, the 0th order solution, plus the first order solution, times epsilon, a parameter, a small parameter epsilon, plus epsilon squared u2, second order, third order, and so on, where epsilon is very small and u0 is the 0th order solution. Now we seek a solution to the first order, u equals u0 plus epsilon u1. So we're going to take this to first order, so it's a 0th order plus first order term here, and we'll take that as our solution, our approximate solution. Alright, so we have u is u0 plus epsilon u1, and u is this object here, plus epsilon u1. So here's the Newtonian solution we saw earlier, plus epsilon u1. We want to find this u1. So we now substitute this into the relativistic orbital shape equation, which we saw on the previous slide, and second derivative here of this object here, this is our solution, our approximate solution, plus u, the solution here, this constant earlier, plus this object here, the relativistic correction term, and in place of u we put u0 plus epsilon u1, all squared. And okay, we'll just separate these here, just simple separation, the u0 part and the u1 part, the constant over here, and then we'll expand this bracket on the right here. So u0 squared plus 2u0 epsilon u1 plus epsilon squared u1 squared. And we get here, we saw it for the Newtonian case, the zeroth order solution is equal to this constant here. And we have the u1 part here, this derivative, and then over the right hand side we have this object here. So this object and this object in the next line, this constant here and this constant here will cancel out, and we'll be left with just this and this, and so writing that down here, here we are, the second derivative of this object, this first order part of the solution, plus the first order part there is equal to this. And that's what we're going to do with this business here. Alright, so we have, here's what we've achieved so far for the first order part. So we're finding the solution here to this object for the first order part. We're seeking to find what is u1. Now we can also see that as epsilon approaches 0, we get, in the brackets here, or parentheses I should say, the parentheses, we have u0 squared plus 2 u0 epsilon u1 plus epsilon squared u1 squared. In the limit as epsilon goes to 0, we're left with just the u0 squared part. Now it turns out that a suitable solution can be found using only the first term above, which is the u0 squared part. Now epsilon squared, epsilon is a very small parameter anyway, so epsilon squared will be much smaller again. So this part is not terribly significant. Epsilon again is a small parameter, so again that reduces this part here, but you may feel taking that out is a bit arbitrary and will reduce the accuracy of the solution, but it turns out, as you'll see later on, that just having this first part, u0 squared, will be perfectly suitable and will give us a very good approximation, as you'll see the example at the end of near the end of the video. So we'll take u0 squared as our solution. And what it means is now we have a constant here, and this will, you'll see shortly how that works out, and we won't have to worry about this u1 unknown here. So then we need to solve this object here in terms of u1 is equal to this constant times u0 squared. Okay, u0 squared then is coming back to the Newtonian solution. The zeroth order was the Newtonian solution, and we want the square of it, so we're squaring all of this. And that gives us, we're going to just make a slight substitution to simplify the variables here, just to simplify with the constants. This entire big constant here, we'll just simplify and call it alpha. So this becomes alpha squared times this squared. And notice there's no u's in here, so it's much simpler for us to work with. Alpha squared times all of this, expanding this out, so 1 squared is 1, 2 times e cos phi here, plus e squared cos squared phi. And coming back now, this is what we seek to solve here, so substituting that in, we get this object here. Alright, just another substitution to simplify our constants a little bit. Let's call k 3gm c squared alpha squared equal to this object here. So all that we can just call k to simplify the equations on the page. Alright, which means that we now have second derivative of u1 plus u1 times is equal to k, times everything in the parentheses here. So we want to solve that for u1. We're looking for a solution u1. Now, from the half angle identities we have e squared cos squared phi. This last term there can be replaced with a half e squared. That's the eccentricity in terms of the orbit we're interested in. So that's just a constant. And plus a half e squared cos 2 phi. So that'll make our life a little bit easier. And we'll substitute that in. So instead of this here, we now seek to solve d2 u1, d phi squared plus u1 is equal to k times, in parentheses, this constant here, 1 plus a half e squared, plus 2e cos phi plus a half e squared cos 2 phi. Alright? Now we need an expression for u1 that, when substituted into the left-hand side above here, gives us the terms on the right-hand side, all of this. Alright, well, just if we had a look at the third term on the right-hand side, can be obtained by was the 2e cos phi was the third term. If we just notice that the second derivative of phi, the ordinary derivative of e, the constant eccentricity, times this variable phi, angular variable phi, sine phi, second derivative of that, plus e phi sine phi d phi, well that's, if we differentiate this, we get d phi is e sine phi plus e phi cos phi, plus e phi sine phi. Differentiate that again, because we just want to differentiate this in the parentheses here twice. And when we do that, we end up with e cos phi plus e cos phi minus E phi sine phi plus E phi sine phi. The two end terms cancel out. These two sum to give us 2E cos phi. And that was the third term on the right-hand side on the previous slide that we had. And the fourth term on the right-hand side can be obtained by, if we take the second derivative, the fourth term was this bit down here. If you have a look at half E squared cos 2 phi, that bit there, that was the fourth term on the right-hand side. Well, bit of guesswork here, but the second derivative with respect to phi, ordinary derivative, minus 1/6 E squared cos 2 phi, minus the same thing again, just not differentiated. If we differentiate that once, we get d phi 1/3 E squared sine 2 phi, minus what we started with. And differentiate that again, we get 2/3 E squared cos 2 phi, minus 1/6 E squared cos 2 phi. So this could be written as 4/6, minus 1/6. Right, gives us 3/6, which is a half. So we have a half E squared cos 2 phi, and that was the fourth term on the right hand side. This one here was the fourth term on the right hand side. This was the third term on the right hand side, and the two terms before that were just constants. So that this object here and this object here can be used in the following way. So we choose as our first order solution to be u1 is k times, remember the constants, 1.5 E squared. Remember this one, minus 1/6 E squared cos 2 phi on the previous slide, plus E phi sine phi. Alright, let's put this constant here back. So we take this to be as our solution. And the first three terms in the parentheses will be very small when multiplied by the constant in front, 1/2 E squared and that. And again this one, E squared here times 1/6 and so on, they'll be very small. The same is not true of the fourth term. If you look at the fourth term here, you've got sine phi, that's going to vary between +1 and -1. But if you look in front, you have the constant E, no big deal, but phi, this angular variable. Now with every orbit, this value will grow, it will accumulate. It's cumulative. With every orbit, it will just grow and grow. And this whole last term here will become the dominant term by far. And it won't take too long to do that. It will just accumulate per orbit. Phi will just keep growing and growing and growing. Right? So we can then disregard the first three terms here and take as our solution, our first order solution, u1, is this constant times E phi sine phi. Because this factor phi here, this variable phi, will grow with each orbit and will become the dominant term by far. So the first three terms can drop out. And it turns out, as I'll show you later on, that's also a very good approximation. Alright, so our total solution is u equals u0 plus u1. So here was u0, the zeroth order solution, the plain Newtonian case, and then the relativistic correction part here. So we have a solution to the relativistic orbital shape equation. Let's do a little bit of algebra now and combine them. Okay, here we go. All this. And we will have this object here, and if we notice here 3g cubed, this is 3g squared, m cubed, m squared, so that's correct there. Remember there's an m0 squared here, times m0 squared here gives us m0 to 4, l squared times l squared, l to 4, and so on with that, okay? So when we simplify this out a bit, alright, we'll call this object, this series of constants here, we're going to call gamma. We'll leave the E there, the eccentricity, so this will be gamma, and the gamma appears down here, so it's looking a little bit simpler now. Then we have this object plus 1, inside 1 plus, and factorise the common factor of E in the last two terms here, E outside of cos phi plus gamma phi sine phi. Now for gamma much less than 1, we're going to make use of some trigonometric identities. Now for gamma much less than 1, okay, we'll have that cos phi, the business here in the parentheses, this part here, cos phi plus gamma phi sine phi is approximately cos phi cos gamma phi. Because remember, for small angle phi, cos phi for a very small angle is close to 1. So, okay, and we have cos phi times 1 here. So this 1 here could be replaced by this for very small angles, approximately that is. And then over here we have sine gamma phi times sine phi. Now for small gamma, gamma times phi will then be very small itself, and for small angles, the sine of a small angle is just the angle itself. So sine gamma phi is the same as just gamma phi for small angles, for gamma very small. Alright, so reasonable approximations there. Alright, we can take this further and we can use the difference of angles formula here, and we have cos of 1 minus gamma times phi is cos phi cos gamma phi plus sine gamma phi sine phi. And as we saw on the previous page, for small angles, for small gamma, cos of a small angle is just 1, and sine of gamma phi for small gamma, or for small angles, sine of a small angle is just the angle, so we can just call that gamma phi times sine phi here. So this line is approximately equal to that one. So our relativistic solution is approximately, should have an approximate sign in here, u is this object here. Okay, now, so what period does this have? Alright, well the period of this is 2 pi on the constant out in front of the angle here, so it's 2 pi on 1 minus gamma. Now you notice that 1 minus gamma will be less than 1. Remember, gamma is very small, but 1 minus that small will make it less than 1. So the 2 pi divided by less than 1 will be greater than 2 pi. So there's a suggestion there, the orbit just doesn't close, because this bit here, 2 pi on 1 minus gamma, is going to be greater than 2 pi, and so the period, if it's greater than 2 pi, it can't close. It's not going to be like the Newtonian case where the solution repeats itself every 2 pi, and you simply have the same ellipse each time. This ellipse is going to rotate because it's never going to close on itself properly. So the angle of precession, now delta phi, will be the difference between this and 2 pi. In the Newtonian case, this difference is 0, gamma is 0, and the solution repeats itself every 2 pi. So what you're going to have, when you do a little bit of algebra, we'll have this is equal to 2 pi gamma on 1 minus gamma is approximately 2 pi gamma, approximately 2 pi gamma. For gamma much less than 1, if gamma is much less, if it's very small here, then this will be approximately 2 pi gamma. Next thing. Alright, so we can express these terms in orbital quantities, in terms of orbital quantities. So delta phi is 2 pi gamma. Remember, gamma was a constant we defined earlier, it was 2 pi times this object here, and just tidy it up a bit, we'll have 6 pi g squared m0 squared on L squared c squared. Alright, here's m0 was our mass here in orbit around this other mass, capital M here, angle phi, r, the radius of separation, perihelion at r min, aphelion at r max, semi-major axis A here, and these quantities down here. Alright, now the orbit equation for the Newtonian case says that u0, the zeroth solution, was 1 on r, was this object here. At perihelion, or r min, 1 on r min is equal to this. Alright, and r min we found earlier from the diagram was r min was a times 1 minus e over here. Let's rearrange this a bit and get a by itself. We end up with a is L squared on this object here. So we flip both sides and then divide through by 1 minus e here. And we shall have this object here, a, and so we can rewrite L squared, the square of the angular momentum, in terms of the particle. Now this is the angular momentum of m0. So the angular momentum is this object here. Next bit, the angle of precession per orbit, then delta phi becomes this object here. Okay, and then substituting for L squared, we can have this, and with some cancelling, because gm and m0, the m0 squareds cancel out altogether. It does not appear in the final result. Gm and 1 gm up top here cancel out. We're left with 6 pi gm on a times 1 minus e squared times c squared here. And so our final result, delta phi, the angle of precession, we'll have a look at that again in a minute, is 6 pi gm, we'll have a look at a picture of it in a minute, 6 pi gm on a times 1 minus e squared c squared. Okay, well that's all equations. let's look at an application to see how good our solution is. So let's apply this to Mercury, period 88 days, the eccentricity 0.2, its mass the mass of the Sun, 2 times 10 to the 30 kilograms, because it's in orbit around the Sun, obviously, that's big M. The semi-major axis, 5.8 times 10 to the 10 meters. Substitute those quantities in. Here we are. We'll get 4.99 times 10 to the minus 7 radians. Now, in 100 years, there are 415.06 periods. In 100 years, how many lots of 88 days you've got this many. Hence the angle precession per century is 2.03 times 10 to the minus 4 radians, or converting that to degrees, pi radians is 180 degrees, so 1 radian is 180 divided pi degrees, you get 0.012 degrees. And in arc centuries, in arc seconds, you multiply that by 60 minutes, 60 arc minutes times 60 arc seconds, you'll get delta phi as 43.2 arc seconds per century. And our approximate solution to the relativistic orbit shape equation is, just reminding ourselves, here it is, this is U. Flipping that to get 1 over R, we get R is L squared on GM M0 squared times all this object here. So if you wanted to plot that for values of GM, you could look at specific cases, and angular momentum and eccentricity, and calculate your gamma and so on like that. But if we just move away from their particular units of GM and so on like that, we factor them out, and then as an example we plot, and this plot here is actually just R is 1 over 1 plus 0.85 cos 0.85 phi. So we set the eccentricity to 0.85 and gamma is 0.15 to give us 0.85, and we get this plot here. Right, you can see how it's precessing, you can see how the semi-major axis, this first ellipse here, then the second ellipse, then third, fourth, fifth. Alright, let's just look at that in a little bit more detail. Okay, so here's the same plot on polar axes, polar plot. R is a function of phi, and here we have a polar plot, and degrees around the side there, and the handy little grid lines to help us picture the image. So there's the same plot again. Now, instead of doing on that previous plot, I think I plotted from 0 to 12 pi, so a number of orbits. Have a look at this. This is one orbit. This is 0 to 2 pi. So here it is. It starts here, and round it goes like that. And look how it comes back. From 0 to 2 pi, it does not close on itself. It hasn't finished yet. It does not close on itself. In the Newtonian case, this would close on itself and come back to where it started, but in the relativistic case, it does not because of the correction term on the end. Let's add another 2 pi to see what happens. There, and it keeps going, so it comes around here, and here's the second lot of 2 pi. And again, it just does not close, and that's a precession. And you can see if you look roughly semi-major axis here, the first one, you go here, it's about 215 degrees. And if you look here, it's about 275. Difference between 275 and 215 is about 60 degrees. So you're looking at an angular precession of about 60 degrees as it goes around. Quite exaggerated, just for the sake of the plot, but to show you that the relativistic correction term on the end causes the orbits not to close, unlike the Newtonian case. And that is it.